Hello and welcome back to the channel. If you're new here, we've been exploring the Unsloth puzzles for efficient large language model training and inference. This is part 3 of our Unsloth series. In the first video, we reviewed the coding challenges from Unsloth's job application, the one with the $500,000 salary. These challenges test your skills in GPU optimization, distributed training, and open-source contributions, and include tasks like optimizing GPU dequantization with Triton, implementing CUDA with FSDP2, leveraging Torch Compile effectively, solving Unsloth's GitHub issues, and optimizing backpropagation memory. Efficient coding and a deep understanding of deep learning systems are key. In the second video, we dived into the theory of 4-bit normal float quantization, NF4. Today, we're tackling coding task 1, accelerating NF4 dequantization. The goal is to make it 15% faster than Unsloth's fast dequantize. To do this, we need to thoroughly understand Unsloth's current implementation. It's a deep call stack, so we'll go step by step, starting from the last function. This isn't just about the competition. These principles are valuable for anyone working with compressed data. All right, let's jump into the code. This is all open source, part of the Unsloth library. The top-level function we call is fast dequantize. It takes two inputs, W quantized weights and out, where the dequantized results will go. Let's trace the execution. Now, to make this call stack easier to follow, I've created a visual representation. Big thanks to Claude for helping me create this little app. We start with fast dequantize, which you can find here. Then, fast dequantize calls cdequantize blockwise FP16NF4, located in the bits and bytes library. Bits and bytes is a crucial library that Unsloth relies on for a lot of its low-level operations. That in turn calls dequantize blockwise FP16NF4, also in Python interface CPP. Next up is dequantize blockwise. Dequantize blockwise calls kdequantize blockwise. This is a CUDA kernel designed for parallel execution. And finally, kdequantize blockwise calls our star of the show, dequantize NF4. This is a helper device function. I put all the links in the description. So here we are, dequantize NF4. This is a device function, meaning it runs directly on the GPU. It's also force inline, a strong hint to the compiler to inline it, paste its code directly where it's called, avoiding function call overhead. The function takes one argument, val, an unsigned char, an 8-bit integer. We're working with 4-bit values, and we'll see how that's handled. This function's job is to take a single 4-bit quantized value and return its corresponding float. The core of this function is a nested if-else structure, a decision tree. Let's break it down. NF4 has 16 possible values, represented by val using 4 bits. First, we check if value bitwise and binary 1000 equals 8. It is essentially checking if the number is greater or equal to 8. The and binary operation compares two numbers bitwise, and the result bit is 1 only if two comparing bits are both 1. So if the check is true, then we are in the positive half of the NF4 values. Otherwise, we are in the negative half. Inside each branch of this condition, another check is made. So basically, each if statement asks, is this bit 0 or 1? Following this path, we uniquely identify which of the 16 NF4 values represents with exactly 4 checks. At the end of each branch, we return the corresponding float. These are predefined NF4 quantized levels. We can visualize it using a dequantized tree visualizer with Claude Artifact. You can check how any number between 0 and 15 is dequantized after 4 bitwise checks. Why is this implementation efficient? It employs several key optimizations to maximize performance on GPUs. First, bitwise operations for fast decoding. The function uses bitwise masking to check individual bits of the 4-bit input. These operations are extremely efficient on GPUs and avoid costly arithmetic computations. The checks are structured hierarchically, mimicking a fully balanced binary search tree, which ensures that each bit is tested exactly once, minimizing redundant operations. Furthermore, the nested if-else structure mirrors the 4-bit values binary hierarchy, allowing the compiler to generate predicated instructions or optimize branch paths. While warp divergence could occur, the fixed-depth tree, 4 levels for 4 bits, ensures predictable execution. It also avoids memory access overhead. Instead of using a lookup table, LUT, which would introduce memory latency, the function directly returns pre-computed constants. This keeps all operations in registers, avoiding global constant memory accesses. It's also notable that compiler directives are used. Force inline ensures the function is inlined at call sites, eliminating function call overhead and enabling further compiler optimizations, such as constant propagation. In summary, this implementation prioritizes register-based computation, efficient bitwise operations, and compiler-friendly structuring to achieve fast dequantization. It balances branch efficiency, avoids memory latency, and leverages GPU-friendly optimizations like inlining and constant usage. That's just our first deep dive into Unsloth's dequantization function. Still many things to learn. We've seen how a seemingly complex task is simplified into an efficient decision tree, utilizing bitwise operations and compiler hints. This shows how low-level optimization can significantly impact performance in demanding applications like LLM training. We'll study the rest of the Sloth's dequantization function in future videos. Thanks for watching, and I'll see you in the next video as we continue our pursuit of maximum efficiency. Don't forget to like and subscribe, and share your thoughts and ideas in the comments.